Okay, let's get going again. So the formalism I've been showing you so far is the more general one, because so far I have not made any assumptions about coordinates. I've been talking about spatial vectors and spatial objects, but everything I've written down still has the Greek space-time indices. So you can actually go through this 3+1 decomposition. You can decompose into spatial and time-like objects without ever choosing coordinates. If we had chosen coordinates ahead of time, all my expressions would have been a little bit simpler, but not very much simpler. But so it was the more general formalism. But now it's time to actually choose coordinates. And if we have our hypersurfaces, and we want to take them as our time steps when we go forward in time, what we want to do is we actually want to use the time coordinate consistent with these hypersurfaces. So we're now choosing coordinates such that x mu has as first component time, and as the other components some spatial coordinates xi. So this t here is the time function from earlier. And this xi are still some, so far known, are spatial coordinates. And so here the I goes over 1, 2, and 3. That now leads to the following picture. We have our hypersurface sigma t, and a point on here, say this point, has the coordinates t, xi. The first one is t because I'm plotting sigma t, so this t is the t from the hypersurface. And the xi is just whatever spatial coordinates I happen to be using within this hypersurface. If I now have a second hypersurface a little bit later, so some delta t later, we get to choose we need to relate the coordinates on the first and on the second hypersurface. So there's also all the points on this hypersurface have a time coordinate t plus delta t, because that is the definition we've put down for our first coordinate number. But we now get to choose which point on the second hypersurface corresponds to the same point xi on the first hypersurface. And so in general, that will be some point on the second hypersurface. And so these 2 points are related with lines of constant spatial coordinates xi. And I've drawn this here at an angle. This choice of how the coordinates on one hypersurface and the next are related to each other is one the user has to make as part of solving Einstein's equations. So now let's try and relate these quantities to some of the earlier quantities that I mentioned in the last hour. One is the normal to the hypersurface. And so the normal distance from one hypersurface to the other one is proportional to n mu, and it has a length of alpha delta t. And then there is this orthogonal piece going here, going vertically. And that piece is a vector beta mu times delta t. So the delta t's show up here just to make all the distances work out. If you're moving the second hypersurface twice as far away, all the vectors should become twice as long. And the direct connection from the first point to the second point up here, this is going to become the time vector, t mu delta t. And so the names that are associated with these objects, let's put them all at the side, is that T mu is alpha n mu plus beta mu, so that's the time vector. Beta mu, or rather just beta I. No, let's stick to beta mu for the time being. Beta mu is the shift vector. Its name comes about because it shifts the coordinates from one hypersurface to the next. And alpha is the lapse function. It relates the coordinate time between the two hypersurfaces, t, to the proper time, as we will see in a little while. Okay, so we have these two important vectors, t and beta, and the lapse function. And we now have a coordinate system where the first index of the coordinate is always just the hypersurface, and the three spatial indices are representing the different dimensions within each hypersurface. Now let's actually work out a few of the coordinate representation of a few of the important objects that we had mentioned earlier. And if you take blue pens here, you should be really quick in removing it again. So, to start, let's look at n mu. Of objects. So, n mu, our definition was minus alpha gradient of time. Time is just a scalar function, so the gradient becomes a partial derivative. And because time is our first coordinate, this actually turns into a minus alpha 0, 0, 0. So n lower mu only has a time component. And that now immediately gives us a lot of cool things about other vectors. For instance, beta mu now must have the form 0 beta I, where this 0 here comes about because beta is a spatial vector. It is orthogonal to the hypersurface, and so dotted into n it must be 0, but n lower index only has the time component, so to make this 0, beta upper mu's time component must be 0. And the same is true for any upper 0 component vanishes. For instance, gamma 0 I is gamma J0 is gamma 0, 0 is 0, because whenever you're contracting spatial tensors with n, you're picking out the zeroth components, and all of these vanish, because the tensor is spatial. And so gamma with the upper indices is actually a matrix that only has a 3 by 3 submatrix of interesting numbers. What else can we do? The next thing we can do is think about the time vector. So T mu has components 1, 0, 0, 0. And that can be seen by the definition of the time vector. It is the vector pointing from the point t, xi to the point t plus delta t, xi. So I can write this as t plus delta t, xi minus t, xi divided by delta t. And the xi's just cancel each other. And in the front one, what remains is the 1. And having the t and having the beta I, we can now work out that the n with the upper index, n mu is 1 over alpha t mu minus beta mu. That's the definition of t. Solved for n. And now we can plug in our other two components here, and we find that it has a 1 over alpha and a minus 1 over alpha beta I. So we are slowly building up a dictionary of the components of the various objects in this particular coordinate system. So one of these blueprints is really bad to erase. I think it's this one. Let's stay away from it. Or rather, let's switch to red. One can also show that gamma ij, gamma jk equals delta ik. That's an interesting expression. The gamma upper ij is this submatrix here. The gamma lower jk is a submatrix of the 4 by 4 full gamma lower mu nu. So if you only take this 3 by 3 submatrix, you disregard the time components, and you plug this one into this type of matrix equation, you find that this 3 by 3 submatrix is the inverse of this 3 by 3 submatrix. And this can now be used to show that gamma ij and gamma ij, upper lower indices, lower and raise spatial indices. So for instance, this gives now that beta with the lower index I is gamma ij beta with the upper index j. And the curious thing to note with this type of expression is that beta with the upper index has a zero time component, but beta with the lower index has in general a non-zero time component. So spatial tensors actually may have time components floating around, but they are usual of no consequence, and the spatial numbers carry all the information. The next thing we can do is to work out what the space-time metric is. So the space-time metric G mu nu is, how do I have this with lower indices? Is minus alpha squared plus beta squared, beta j, beta I, gamma ij. And showing this takes about 3 to 4 lines of algebra. It's not a particularly hard calculation.
So you can give me some why the variant beta is a component, time component different from 0 and the covariant is
Good question. So this one here is 0 because beta nu and mu is 0, and the n with the lower mu only has a time component. So therefore this number must be 0. The beta lower mu is G mu nu beta upper nu, and so the beta t will turn into a G T nu beta nu, and this just is whatever it is.
And there is no particular consequence of this.
No. You can compute the beta t like this, and you can compute the beta I either by Chi nu beta nu or by gamma ij beta j. And that happens to be the same answer. Because first beta nu 0 vanishes, so you only have the Chi ij terms here. And for the lower Chi ij, the spatial components are identical to the gamma. The more curious thing is if you now want to go back. If you want to go back and trace the index again, you can play this game twice in two different ways. You can get the B upper mu as a G mu nu beta mu. And what you will find out of here is that the time component is 0, and the spatial components are whatever they are. But you could also, to get here, you need the G 0t beta lower t term. This is part of what's forming the beta I. Or you can get the same result by computing beta I equals gamma ij beta j. And this is now different from this calculation in that I'm only using the spatial parts of beta j. I don't use the beta t. So you would get a different answer. But this difference is compensated by using the spatial metric gamma here, which is not the same as the spatial metric, as the space-time metric g with the upper indices. They are different from each other.
Yeah, this G, the G 0, 0 is different from 0, right? G
Yeah.
Because if you see in the right-hand side, in the left-hand side, B with 0 index up, you would have to contract with the If mu is equal to 0, then you would have G of 0 contracted mu there. But if G 0, 0 is different from 0 and beta with 0 down is different from 0, how you get to 0 first component?
So the reason why this works out is because Gij with upper indices is not equal to gamma ij with upper indices. Gij with lower indices is equal to gamma ij with lower indices. I will regret this, but I'm doing it anyway. I don't have this in my notes, but since you're asking about this, let's try and
We can discuss this later.
yeah, let's try and compute G with upper indices. This is gamma with upper indices plus, and is there plus or a minus? There's a minus. So this is and we have gamma sitting here, and we have n sitting here. So we can combine these terms together, and let's see what we get. Time, we don't have any gamma. And from n, we have the 1 over alpha squared. Times...
Minus.
Yes, you're absolutely right. Times space, up here, we still don't have any gammas. We have 1 over alpha and 1 minus 1 over alpha beta. So we have a 1 over alpha squared beta I. That is also going to be down here. And in the space part, we have the gamma ij. And then we have this term here squared with a minus sign, minus and minus. 3 minus signs gives us a minus sign. Minus alpha squared beta I beta j. And so this thing here are the spatial components of the upper space-time metric. And it's this extra term that makes the transformations over there work out. Once with and once without the b lower t. Okay, having g lower ij, we can now write down our space-time interval as just xing this thing out. We have a minus alpha squared plus beta squared dt squared plus 2 beta I dxi dt plus gamma ij dxi dxj. If you rearrange parentheses, this turns into a minus alpha squared dt squared plus gamma ij dxi plus beta I dt dxj plus beta j dt. And this is now the metric in 3 plus 1 form. The other thing now in this particular coordinate system is that all spatial objects collapse into their usual definition in a coordinate basis. So I've already indicated over there that beta mu can be replaced by a beta I, and that beta mu can be replaced by just beta lower I. And the time component doesn't really carry extra information. It can always be reconstituted by the fact that the whole beta 4 vector must be orthogonal to M. We also have that the extrinsic curvature turns into a 3-dimensional object, Kj. We have derivatives like d mu of v mu. They are going to turn into a di of vj. And this di of vj turns out to be the usual definition of covariant derivative. It's the partial derivatives, only along the spatial directions, plus Christoffel symbols. And these Christoffel symbols are defined the usual ways as you would define Christoffel symbols based on the spatial metric. Gamma L k comma I plus gamma I L comma k minus gamma I k comma L. So once you adopt coordinates, all the spatial things just become usual differential geometry with one fewer dimension. And now we have all the pieces in place to actually talk about Einstein's equations. And we are now also decomposing Einstein's equations into space and time components. So the Einstein equations are the four-dimensional Ricci tensor minus 1/2 the four-dimensional trace of the Ricci tensor equal 8 pi t mu nu. And as before, we keep on defining orthogonal and projected pieces. We haven't done so for the sparse energy tensor yet, so let's do this. If you project twice normal to the surface, you get the time component, the rest mass energy. If you project once, mu gamma mu prime, you get a momentum density. And if you project twice, you get the spatial piece, the momentum flux. And now we can play the same game, taking projections of the Einstein equations themselves.
Is this only true in this coordinate system you're using?
Yes, so these definitions depend on the coordinate system only to the extent that they depend on n. So this would be the energy density observed by an observer that is moving parallel to n. And so if we now take Einstein's equations and project it twice with n, we get terms like 4r mu nu, n nu, n nu. And before the break, I was writing down Ricci equation, Codazzi equation, and these other really nasty long equations. Those can then be worked in here to simplify these terms. And what one finds for the contracting Einstein equations with twice n, what one finds is an equation that starts with the three-dimensional Ricci scalar. It has k squared and it has kij squared. And on the right-hand side, t mu nu dotted into two ends is going to give us rho. And there's an overall 1/2 that is being added into the mix. So this is going to be a 16 times rho. There's one extra term I haven't defined yet, which I will do later. And this is the symbol k. K is the trace of kij, kij dot gamma ij. If you work in one time and one space component, and gamma, you get an expression back that has one free index, one spatial index coming from the gamma. And that happens to be the spatial derivative of kij minus gamma ijk equals 8 pi si. If you take two gammas, you find an equation that has the time derivative of kij. So this is where the second time derivatives show up that I pointed out just before the break. And the right hand side here is quite nasty. It's alpha 3ij minus 2 kik k kj plus k kj minus di dj alpha. Then there are terms that have matter in it, minus 8 pi alpha Sij minus 1/2 gamma ij S minus rho. And then there are terms that have the shift in it. Beta k dk kij plus kik dj beta k plus k kj di beta k. Okay. So these are the three equations you get from the Einstein equations. And there's two other really important equations that I'll put here on the same whiteboard, which we already mentioned beforehand. One of them is the definition of extrinsic curvature. We had earlier on, when I was introducing extrinsic curvature, we had an expression kij equals Lie derivative of gamma. And at that point, I mentioned the Lie derivative of gamma is essentially a time derivative. And so, in this particular coordinate system, this Lie derivative of gamma indeed turns into a time derivative of the spatial metric. And indeed, it has an extrinsic curvature on the right-hand side. And a few other terms. dj beta I. And this whole thing is finally coupled with the metric ds squared is minus alpha squared dt squared. This is an expression I had already spelled out earlier. dxj plus beta j dt. Okay, so and what we now have here on this blackboard, this whole set of equations goes under the name of ADM equations. This is now the fundamental decomposition of Einstein's equations, such that we can begin thinking about hypersurfaces and moving forward in time. And so we'll spend the next 10 minutes discussing the structure of these equations and how this might help us moving forward. So first of all, let me point out or remind you, ADM stands for Arnold Desser Missner, who in 1962 did not write down these equations. It turns out ADM wrote these equations not in terms of Kij, but in terms of the conjugate momentum to gamma ij, which has a few extra terms in it, which actually matters every now and then for some aspects. But the actual form of these equations with the Kij's in it, this comes from Jimmy York, 1979. As a little bit of historical perspective. The differences are quite minute, but this particular set of equations is not in ADM. Now, what do we have? Let's discuss things. Let me first remind you that on this blackboard, everything, all variables, are functions of space and time. Space plus time. So it's a different, everything is dependent on space and time. It looks like that Kij and gamma ij are evolved variables. So you have equations here that give you the time derivatives of Kij and gamma ij. And so it looks like we have a set of evolution equations that, if we know everything at a certain time, we can use the two evolution equations, dt here Kij, dt gamma ij, to tell us how these quantities look like. So specify at t0 and then evolve to t bigger than t0. The quantities alpha and beta show up in these equations in various places. Here's an alpha, here's an alpha, here's beta. Alpha and beta show up in these equations, but never as time derivatives. They're actually freely specifiable. The alpha and beta determines how the coordinates evolve as you go forward in time. You start at some hypersurface T0, and then what you mean by the hypersurface T1 will depend on how you choose alpha to move forward in time, and you have spatial coordinates xi on the initial size, whatever they might be. But what you have at xi on the later time will depend on how you choose beta. And so the alpha and beta doesn't tell you anything physical about the solution, it just tells you what coordinates you end up having later on. And then there's two more equations that I haven't mentioned yet. These ones here, let's call them H and M. H stands for the Hamiltonian constraint. And M stands for momentum constraint. These two equations, H and M, do not contain any time derivatives. So, when we think about writing down data at t0, we better choose Kij and gamma ij that satisfy these two equations. Otherwise, we have inconsistent initial data and can't evolve at all. So H and M do not contain time derivatives. They restrict the choice of permissible Kij and gamma ij. And these restrictions happen in every hypersurface. Sigma t. So these are called the constraint equations. Okay, so far so good. It looks like we are as good as done. There begins to emerge a way of evolving Einstein's equations. Step number one, figure out some initial gamma ij and Kij that satisfies the constraint. Step number two, choose alpha and beta, lapse and shift functions. Step number three, evolve the time equations. And that then will give us an answer.
If you choose the initial data and you evolve it, are you guaranteed that it will always still obey the constraint equations, or is that something else you have to do?
You guys are smart. Yes, it will. And I have a note here, and I decided I'll skip that note. It turns out, if you start with initial data that satisfies the constraints, and you perfectly satisfy Einstein equations as you go forward, the solution will continue to satisfy the constraints. However, if you start with initial data that is off by epsilon, it may happen that this epsilon grows exponentially and your constraint violations grow exponentially. So I've sketched this little plan of how to solve Einstein's equations. Let's put it down. Okay. So it looks like a plan. One, solve constraints. Two, pick alpha and beta as a function of x and t. 3, evolve dt gamma ij, dt kij. Okay. The difficulty here is, there's still a lot of difficulties. One difficulty here is that Hamiltonian momentum constraints, as written over there, are of no known form. Mathematical form. So it's actually not clear just yet how you would go about solving the constraints at all. When you're picking coordinates, you must pick coordinates for a space-time you don't know yet. So this point is also quite difficult. So here the difficulty is how to choose the coordinates without knowing what's going to happen. And down here, for this third point, the difficulty is that these two equations here are only weakly hyperbolic. And if you remember from yesterday, weakly hyperbolic means not good. So we have a plan, except that every single step of the plan needs a lot of extra work.
Sorry, what do you mean by mathematical form?
This is not yet an equation that mathematicians would know how to constructively find solutions for.
In general, or like, can you pick certain? Like, sorry.
You can make wild assumptions and guesses, and if you make enough simplifying assumptions, you will find some solutions. But how do you go about finding all possible solutions that exist? So you're looking for 12 free functions, Gij and Gamma Ij. We have 4 equations that restrict them. So there should be in total of 8 dimensions of in the parameter, in the solution space. And how one actually goes about writing down procedures that can reach all these possibilities in a well-defined way, that is not yet clear if you just have these 2 sets of equations. Okay, let's, the next 15 minutes until we go into the break, begin working out how we're going to solve the constraint equations. Because if we don't know how to solve the constraints, we can't really do much at all. And especially, things like flat space would be easy to write down to solve this, but how do you find solutions that, say, have 2 black holes with certain linear momentum and certain spin? That's where we want to go to. When you're solving the constraints, the basic strategy is divide and conquer. We want to decompose gamma ij and kij into more distinct pieces, such that some of these distinct pieces are mathematically meaningful determined, and the rest of them is free for us to choose. It turns out step number 1 is a conformal transformation. You write the physical metric gamma ij, which is a function of space, as a conformal factor to the 4th power times a conformal metric, which can also be a function of space. So we're just splitting up an overall multiplicative factor of the metric. And at that point, with the second metric, we can write down a conformal differential geometry. We can define an upper conformal metric. That is the inverse of the lower one. We can write down conformal Christoffel symbols. We can write down a conformal derivative operator. We can write down conformal I, J, K, L, conformal curvature quantities. All of these are determined with the usual differential geometry formulas, just based on gamma delta instead of gamma. Why would you want to do that? The reason is that it turns out that the three-dimensional Riemann scalar of the metric gamma ij is equal to psi to the minus 4 times the conformal trace of Ricci minus 8 psi to the minus 5 times the conformal Laplacian acting on psi. This equation is now really nice because it relates the three-dimensional R to the Laplacian of psi, and the three-dimensional R happens to be the most nasty term in the Hamiltonian constraint. So if you plug this one into the Hamiltonian constraint, we have the Laplacian of psi. We can solve for the Laplacian of psi, and we get an equation that looks like Laplacian of psi minus a lot of other terms plus psi to the 5 over 8 kij minus k squared equals minus 2 pi psi to the 5 rho. So what we can now do is we can choose gamma delta. We choose this conformal metric. Everything here, the R delta is known. So all the terms here are now fine. And we can then solve an elliptic equation for psi. So that way we have transformed the Hamiltonian constraint that we didn't know how to solve into something where we now have an algorithm to solve. We first pick a conformal metric, and then we have an elliptic equation, quite complicated but still an elliptic equation for psi, where the elliptic equation we know from mathematical theories will have a unique solution.
Do we get a solution in terms of k, or is...
Good question. So right now, as far as I have written down the algorithm, in order to solve this, we also need to know k, which we don't know yet. So where this is going to is we have to solve the current set of equations, one for psi and 3 more for k, all combined with each other. But before going there, let me make a little side remark. To show that all the stuff that we are doing here actually is useful.
One question.
Yeah.
For the when you say choose the conformal metric, you are choosing also the lat and the shift vectors for the initial slide. No?
So far we are talking only about the initial conditions. We are only worrying about the momentum constraint and the Hamiltonian constraint. And we're not yet worried about the time evolution equations. So we're not yet talking about time evolution, so we don't need to worry about lapse and shift just yet.
But at t equals 0, you have to specify the shift field, no?
At t, if you want to evolve, in order to evolve, you need two things. You need the initial gamma and k, and you need to choose alpha and beta. Right now we are trying to get the gamma and k. And then later we need to worry about the alpha and beta. Luckily this is separate from each other.
Just as a follow-up question, so if I want something in a quasi-circular orbit, I still need to choose my shift, also at that level?
Yes. You still have to choose your shift. No, actually not necessarily. If you have, so gamma ij and k ij completely determines the solution. If you were to know gamma ij and k ij for two black holes in a circular orbit, you have two black holes in a circular orbit. If you now choose a nice lapse and shift, the circular orbit looks like a circular orbit. If you choose a ridiculous lapse and shift, you get a coordinate system where the black holes might do really strange things in coordinates, but it still represents the same circular orbit. And if you look at the gauge invariant gravitational waves, you still would get the same gravitational waves. Whether with a really stupid lapse and shift the computer can solve the equations is a separate question, but in principle, those are independent questions. Okay, my side remark is as follows. Let's pick vacuum. And let's pick Kij equals 0. So vacuum means the right-hand side here is 0. Kij equals 0 means the left-hand side is 0. So the momentum constraint is solved. And the Hamiltonian constraint I've just erased, unfortunately. The Hamiltonian constraint simplifies into a, oh no, I still have it over there. It simplifies into a covariant psi squared equals 1/8 psi r. Now let's assume conformal flatness. So we have gamma ij is the flat metric Fij. And how this looks like depends which coordinate system you're in. If you are in Cartesian coordinates, this would just be delta ij. If you're in spherical coordinates, this would be 1 r squared sine theta as a diagonal matrix. Doesn't really matter which one you're choosing. But if you now choose a flat coordinate metric, then the Hamiltonian constraint simplified further, the Laplacian just becomes the flat Laplacian. And the right-hand side becomes 0 because our trickle is 0. And this is now an equation where most of you should be able to tell me some solutions.
Harmonic functions.
Harmonic functions, exactly. In particular, the harmonic function I want to take is psi equals m over 2r plus 1. I'm putting in the plus 1, so I have psi goes to 1 at large distances, and there's a 1 over r, and Laplacian of 1 over r is 0. So in this equation, m is a constant, and r is the plain old Cartesian coordinate distance. If you now work this out, the metric I now have is psi to the 4, and then there is whatever there is. For instance, dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. This is the Schwarzschild black hole. This is the Schwarzschild solution in isotropic coordinates. So this whole formalism, as different as it might seem, can actually now reproduce the usual black hole solutions. And Schwarzschild, by essentially solving a flat space Laplace equation. But we can do better. We can also write down psi equals m1 over 2x minus x1 plus m2 over 2x minus x2 plus 1. And this now is a two black hole solution with both black holes at rest. And it's precisely this down here, this type of solution, that I was mentioning yesterday morning when I was pointing out that in 1964 the first black hole evolution happened. They were using this type of initial data and then trying to use the computer to see what happens. So we already have quite some power in solving all our equations. I think I ran over time yesterday, so it might be good to stop here and postpone how to deal with the momentum constraint to tomorrow. Thank you very much.